Howdy guys. So today we are going to be talking about volumes. You remember that was what we were introducing last time at the end, and I do want to pick it up there. But before we pick up with the mainstream of the lecture, if there are any homework questions that were bugging you from homework 1, which was due today, just at the start of class, so just right now, we can take a look at those first. I did see this morning that there were a couple extension requests, and I went ahead and granted those. I'm not sure if there are any fresh ones. I'll take a quick look. Yeah, there are a few of them, so I will go ahead and grant those as well as soon as class ends, and then open up the new homework. But for the time being, are there any questions from that first homework that you guys would like to look at before we start moving on? So before we move on to the volume stuff. Yeah. 11 and 19. Okay. All right. So number 11 asks us to evaluate the definite integral from e to somewhere to e to something else. So I've got e to the 4 to e to the 64 of 1 over x times the square root of ln x dx. So let's swap back to the dot cam. This is what we want to do. They wrote it as dx over x times the square root of ln x. I always like to pull the dx off to the side, but it's the same thing. And your limits might be a little bit different. The limits that I got there when I loaded them were these, but there's some random number stuff built into the WebAssign. So if your limits of integration are a little bit different, that won't change the problem solving technique at all, but it might change the answer. So what I see here, and if you're having a hard time spotting it, is this. I think of it like this, because if not for the ln x there, this would be a relatively easy integral, right? If it was just 1 over the square root of u or 1 over the square root of z, I know how to handle that. And the 1 over x is exactly the piece that I need in order to substitute for ln x. So this is a substitution, and I'm going to let z be the natural log of x, which means dz is 1 over x dx, which is why having this x here, this 1 over x here, is so nice. The other thing I need to do is, of course, change my limits. So when x is equal to e to the 4, z will be the natural log of e to the 4, which is just 4. And when x is equal to e to the 64, z will be the natural log of e to the 64, which is just 64. So this is my little substitution box. It's got all the stuff I need. And when I employ that substitution, I get the integral from 4 to 64 of 1 over z dz. So that's the natural log of the absolute value of z evaluated between 4 and 64, which is the ln of 64 minus the ln of 4 And then you can use, so it would be okay to stop here, but you can also use properties of logarithms to combine this. This is the ln of 64 over 4, which is the ln of 16. So that is how that one shakes out. It's a relatively straightforward substitution problem, but you need that 1 over x dx in order to make it go. Without that 1 over x, this would never work, because I wouldn't have the piece I need to make my substitution go in, or at least it would be much harder. Any questions about this? Oh, shit. Oh, whoa. All right. This is a teachable moment. I fucked up. Where did I fuck up?
You forgot the square root.
Yeah, this is my bad. Yeah, sorry. So this should definitely be a 1 over the square root of z here. Does that mean this becomes the natural log of the square root of z?
No, it's z to the negative 1/2.
Good, right. Yeah, all of this is out. This is now a power rule integral. So I'm very sorry about that. But yeah, this piece is our dz. This 1 over square root ln x is 1 over square root of z. So this is the integral from 4 to 64 of z to the negative 1/2 dz. Yeah, and now that's a power rule thing. So I'll add 1 to the power and divide by the new power. That's z to the 1/2 divided by 1/2, or 2 square roots of z, which we need to evaluate between 4 and 64. So that's 2 times the square root of 64 minus 2 times the square root of 4, which is 2 times the square root of 64 is 8, minus 2 times the square root of 4 is 2. So that's 16 minus 4 is 12. Yeah, sorry about that. Sorry about that. But what we said earlier is still true, right? Substitution piece is the important thing here. I recognize that this ln x is what's making things a little bit complicated, and that this 1 over x is the derivative of ln x. So it's what I'll need to make my differential term go through. And if it doesn't jump out at you right away how to do that, you might consider rewriting the integrand with the 1 over x over there next to the dx. And then don't do what I did. Don't forget to write the square root. Sorry, my cats are being a little bit difficult. Nova, are you being nice? Can you be nice to her? Okay. Any other questions on this guy? Okay, we also wanted to see 19. And then we'll talk about some volume problems. So homework 1, problem 19 is asking us, oh, this one again. Yeah, so we've done this one a few times. I'll run through it one more time. So we did this, I think, last Wednesday, and then we talked about it a little bit last Friday. We want to, I'm not going to write every last little thing in here. We're given the curve 3 over x, which looks like 1 over x, just stretched up vertically by a factor of 3. So that's this guy. We're given the curve y equals 12x and the curve y equals 1/3 x. So y equals 12x, that's a line through the origin with a steep slope. And then y equals 1/3 x is a line through the origin with a very shallow slope. And I want to find the area enclosed here. So this area. So that looks like this, right? Here's 3 over x, here's 12x, and here's 1/3 x. In order to set up the necessary integrals, I need to know these intersection points. This one down here is clearly 0, 0, but the other two are not super obvious, and to find them, I need to set 3 over x equal to 12x. So to find intersections, we solve 3 over x equals 12x. And this is a rational equation. There's a bunch of ways you can solve it, but the fastest one is to just multiply both sides by x. So that gives me 3 equals 12x squared. And then I can divide both sides by 12. So I get 1/4 equals x squared. And then I can take square roots on both sides, and I get 1/2 equals x. I get a plus and minus 1/2, but I'm clearly only interested in the positive solution here because I'm working in quadrant 1. But you could say, okay, plus and minus. But that tells me that this guy has x coordinate positive 1/2. And the y coordinate I could get by plugging positive 1/2 into either of those curves. If I plug positive 1/2 into y equals 12x, 12 times 1/2 is 6. So this is 1/2 comma 6. That's that point up there. And then I do the same thing, setting 1/3 x equal to 3 over x to find the other intersection point. And the same sort of thing, I'll multiply both sides by x here. I'll actually multiply by 3x, and that will give me 9 equals x squared, which tells me that plus or minus 3 is equal to x. So this guy right here has x coordinate 3. And the y coordinate I can find by plugging into either of those curves. Again, the easier one there is the linear one, but 3 times 1/3 is definitely 1. So here's our picture, and it's got all the stuff that we need now. The trick is to remember to integrate upper minus lower. Here, all of these curves are given y as a function of x, so it makes more sense to do the dx integral. You could set it up as a dy integral, but it's going to be more work because you would have to solve each of these equations for x, and then set up the integral in terms of a right minus left thing. But it's already in the right, clean situation here where we can set things up in the upper minus lower. So my area, the only trick is I have to remember to do the stuff. If I look at this guy, this region, who is upper and who is lower depends on where you're looking. So right here, we're going to have to split up the integral. To the left of this vertical line that I've just drawn in, this curve is my upper and this curve is my lower. To the right of that vertical line, this curve is my upper and this curve is my lower. So this guy, remember, is 3 over x, and this guy is 12x. So from 0 to 1/2, my upper is 12x and my lower is 1/3 x. And that'll give me the area over here to the left of this vertical line. And then to that, I need to add the integral from 1/2 to 3. And now the upper is 3 over x, and the lower is still 1/3 x. Okay, so this is the setup. Any questions about how we're arriving at this setup? So this integral represents this area, and this integral represents this area. Together, they give us the total enclosed area, and neither integral is especially difficult. An antiderivative for 12x is 6x squared, minus an antiderivative for 1/3 x is x squared over 6. And I evaluate those from 0 to 1/2, plus an antiderivative for 3 over x is 3 times the natural log of the absolute value of x, minus an antiderivative for 1/3 x is still x squared over 6. And this piece gets evaluated from 1/2 to 3. So I can move this down a little bit, and we can continue our work. That first piece, if I go ahead and do the evaluation, 6 times 1/2 squared is 6 times 1/4, minus 1/4 over 6. And then from that, I need to subtract 0, right? Because I get 0 when I plug in 0 to both of those. And then evaluating the second piece, I'll have 3 times the natural log of 3 minus 9/6. And from that, I need to subtract 3 times the natural log of 1/2 minus 1/4 over 6. Now, there's a lot of minus signs. We have to be careful that we don't get lost in the distribution of negatives. But as long as we go slow and we're careful, we'll be just fine. 6/4 is the same as 3/2. And 1/4 divided by 6 is the same as 1 over 24. So that's that first box. And then from the second box, I have my 3 ln3 minus 9/6, which is the same as 3/2 again, right? Is it? Yeah. Divided by 3, yeah. And then I'll have minus 3 times the natural log of 1/2. And then this minus will distribute and make that other minus a plus, and that'll be a plus 1/24. So just starting to simplify the bracket stuff. What we see is that there's a lot of cancellation. Each of these terms here has a similar term over here, but of the opposite sign. So we don't need to have a common denominator and like try to glue all the fractions together if we recognize that this piece gets chewed up by this piece. And this piece gets chewed up by this piece. So what survives are just the natural log terms. We get 3 log 3 minus 3 log 1/2. That's interesting. And you might be curious if there's anything you can do with the rules for logarithms to further simplify. You can. If you want to, you could write the minus 3 ln 1/2 as a plus 3 ln 2. because the natural log of 1/2 is the same as the negative of the natural log of 2. Factor the 3, and you get ln3 plus ln2. So if you are feeling fancy, you could write this as 3 times, and then the ln of 3 plus the ln of 2 is the ln of 6, using that rule that says addition outside on a logarithm is the same as multiplication on the inside. So that's as nice as this could possibly be. If you leave it at this, I would be perfectly happy, though. There's nothing wrong with this. You should simplify to that point. A fair question would be, well, why is all the fraction stuff going away? And it's not entirely obvious, but you have this x squared over 6 being evaluated at 1/2, and here you have this x squared over 6 being evaluated at 1/2. So that's why those two pieces vanish. And then this piece combining so nicely with this piece is really just a coincidence as far as I can tell. But it does work out that way. So this is a cool problem, and it's probably designed like that. So you see it all collapsing and you recognize that you're on the right path, that something nice is happening. The big trick is to draw this picture and then realize that your upper and lower is different from 0 to 1/2 than it is from 1/2 to 3. So who is the upper function and who is the lower function depends on which part of that region you're looking at. In the region A1 here, the upper function is y equals 12x. And in the region A2 here, the upper function is 3 over x. Any questions on this guy? This is a good test caliber problem. This is about the level of difficulty, if I were to put an area between curves problem on a test, that you would expect to find there. And the way it would usually break down is about 1/3 of the credit would go to the picture, about 1/3 of the credit would go to the correct integral setup, and then about 1/3 of the credit would go to the correct evaluation. Okay. So normally today I do have an office hour. Unfortunately, my cat got hurt last night while she was out, and I have to run her to the vet. So if you do want to go over this problem in more detail, send me a Canvas message with a picture of your work, and I can give you some feedback, and then we could schedule a separate office hour. But I won't have my normal office hour today because, yeah, I gotta run the kitty to the vet. I know it's a bit of a pain in the ass, but sometimes we gotta do these things. The antiderivative step isn't too bad here. The 12 is going to come along for the ride, but then x integrates to x squared over 2. So the x squared is this x squared, and the over 2 makes the 12 a 6. The 1/3 x is going to integrate to 1/3 x squared over 2. And so that's the same as x squared over 6. I could have combined these before I found the antiderivative. I'm just being sloppy here. And then on this side, 3 over x, that's the same as 3 times 1 over x. And the integral of 1 over x is the natural log of the absolute value of x. And this 1/3 x, just like this 1/3 x, integrates to x squared over 6. But yeah, if you want to talk more about this, go ahead and snap a photo or two of your work and send it to me as a Canvas message. And then I'll be able to give you some genuinely useful feedback. I do want to get on to our main topic this week, which is volume. So we're going to start in section 6.3. 6.2, yeah. The two sections are 6.2. And in section 6.2, we're going to talk about two methods. There's the method of slicing, a special case of which can be called the disk/washer method. So there's really just two methods, the slicing method and the disk washer method. Some people think of the disk washer method as two methods on its own for a total of three, but really these are all the same sort of thing. And then in 6.3, no, 3 ln x is not the same as ln 3x, but 3 ln x is equal to the ln of x cubed. Yeah, Fernando's correct, yeah. 6.3 then, the method that we introduce here is called cylindrical shells. And it's just a single method. So we introduced the slicing method last Friday, and that's where we're going to start. So I want to just kind of remind you the basic idea there. Last time we looked at it with a cylinder, but this time I'm going to assume that we just have some kind of wonky looking, vaguely cylindrical object. You know, maybe it has some rotational symmetry, maybe it doesn't. But you put this thing along an axis. And I'll call this the x-axis. So this is 6.2. And I'm talking specifically about the method of slicing right now. If this object starts at x equals a and ends over here at x equals b, and I can find a formula for the area of a cross-section, then I can imagine taking a tiny differential thickness slice. So this is a dx thickness. I think of that slice as being taken at x. And I think of this area of the slice, the cross-sectional slice, as a of x. And you can see if I move this slice around somewhere else, a of x might be a little bit smaller, right? Like a of b, the cross-sectional slice at this end, is clearly a little bit smaller than over on this end. And it could vary, you know, and wiggle around. It goes in and then out and then back in. But the main idea is that if I can come up with a formula for a of x, then I can find the volume of this solid as an integral. So the way I usually do this is I take this slice out of that context. It is a tiny little differential thickness solid. So I call its volume dV. And this area here is a of x. So this tiny solid has volume dV equals a of x, the cross-sectional area, times the thickness. Main point here being that I'm taking my slice to be so thin that I can assume the sides, the top here and the bottom there, are straight lines. Even if the whole solid isn't made up of straight lines, even if these boundaries are curvy, if you take these slices to be small enough, you can get a very, very good approximation for the overall volume by assuming it's made up of straight line solid slices. And in the limit, as dx goes to 0, you will get the actual volume. And that's what we do when we do calculus, right? So we're not setting up a Riemann sum, we're just going to jump straight to the integral. Yeah, like a cucumber slice. Yep, exactly. So if you were to take a cucumber and slice it into a bunch of little slices, each one of those little slices you could find the volume of by taking the area of that cross section and multiplying by the thickness. Then when you add up all of those little volumes, you get the whole volume. The integral is what's going to do the adding up. And then we'll find that there are a few special cases of this type of scenario where you can have a formula that will work pretty consistently for you. So that's our goal for today, is to get you guys comfy with this method of slicing. And the two kind of generalizations, or not generalizations, sorry, special cases of it. So let me grab some fresh paper, and we can start working on some examples. Start off kind of gentle. That's a little tough, isn't it? So most of the solids we're going to work with are going to have a lot of rotational symmetry. And we'll begin with this guy. So suppose I rotate the region bounded by y equals the square root of x from x equals 0 to x equals 1 about the x-axis. So I take my good old square root function, which looks like this, from x equals 0 to x equals 1. I take this region and I spin it around like that. That's going to sweep out a solid that kind of looks like a sideways bowl. It's a, what is this called? It's a paraboloid, I think, is the name of the solid here. So you're going to end up with something that looks like this. Right? So here's my solid. I want to find the volume of this solid. And if you think about it, this x-axis runs right through the middle of that solid. So this is very much like the picture we were just looking at. Here is x equals 0, and over here is x equals 1. And what I want to do is imagine slicing this thing. So I'm going to draw in my slice. There's my slice. The thickness of this slice is dx. I always imagine a differential thickness slice. And I need to find the area of the cross section here. And I'm thinking of this slice as being taken at a point just x. It's a generic point. So can I find the area of that little slice? And what I like to do is I do two things. One, I like to do some drawings over here that help me see what's going on in this picture. And then also I like to redraw just the slice on its own out here and label everything. I recommend you do the same. So here's just that slice. This thickness is a dx thickness. I'm after this cross-sectional area, A of x. And in order to get that, I'm going to have to think about where that slice is coming from. And the trick is to come over here and to draw in a little strip. Because if you rotate just this little dx thickness strip, you will get this little solid. And if this strip is occurring at the generic point x between 0 and 1, then the radius of this disk, right, this slice here is really a disk, is the length of this strip. So if this guy has radius r, then this distance right here is r. And the area there, when you rotate that strip, this thing you get is a disk shape, meaning its cross-section is a circle. That will be pi times that radius squared. But what is that radius? So take a second. Remember, in your notes, you always want to make sure everything I put here on the dot cam really does belong in your notes, especially the first few examples from each section. And then think for a second about how I can express that radius as a function of x. It is, yeah, it's the output from the function. It's the y value up here, right? It's this y value minus this y value. Well, this point is x comma square root of x, because it's a point along the graph y equals root x. And this point down here, this is x comma 0. So the radius, the height of that strip, is root x minus 0. So this is pi times root x minus 0 all squared, which is, of course, just pi times x. Right. So we think of this strip as occurring at a generic point x in my region, which means that the y value along the graph is f of x, which is just root x. And so this total height is root x minus 0. If I was rotating about some other line, then the height might be different. That bottom point might not have y coordinate 0, but here it does. dV then, the little differential volume, or the volume of this little differential slice, is a of x dx, which is pi x dx. Therefore, my overall volume is going to be the integral of dV taken from the smallest x value in my region to the largest x value in my region. So that's going to run from 0 to 1. And then what was dV? It was pi x dx. So this is integral 0 to 1 pi x dx. R, in this case, and in many cases, yeah, R will always come from thinking about the two different y values. R here is the height of this strip. And the height of that strip is not just determined by the y value here, it's also determined by the y value at the bottom. Since we're rotating this about the x-axis, the height at the bottom is 0. But you could imagine that I wanted to generate this solid by rotating about the line y equals -1, which would give this bowl like a flat bottom. And then my radius would be root x minus -1, or root x plus 1, which would change things. So here the radius is always going to be the length of the strip. That's the safe way to think about it. And in this particular case, because the strip's bottom is down here at 0, it's just the y value there. Now this integral is not difficult to compute. The pi comes out, and you get x squared over 2. So this is pi times x squared over 2 evaluated from 0 to 1, which is just pi over 2. Yeah, good. So this is a slicing problem, but it could also be seen as what we call the disk method, or as a disk problem. We'll look at a little bit more of this here in just a second, but before I do so, I want to look at one or two more kind of easy or tractable examples where the slices have a slightly more complicated shape, or at least the shape isn't as obvious. So pi over 2 is the volume. Yep, pi over 2 is the volume of that solid. So the volume is always the integral of dV taken from the smallest value to the largest value in your region. Here dV turns out to be best expressed in terms of x. So I take my integral from the smallest x value in the region to the largest x value in the region. So that's from x equals 0 to x equals 1. And then my dV is just pi x dx. The pi is a constant. So the x dx integrates to x squared over 2. And I evaluate that between my endpoints. When I plug in 0, I get 0. When I plug in 1, I get pi over 2. So yeah, pi over 2 is my volume here. Any other questions on this example? Pi over 2 is the volume of the whole thing. So the volume of this thing, the volume of the slice is just dV. And to get the volume of the whole thing, I integrate all of the slices. I add up the volume of all the slices, which is done by this integral. So this statement right here, V equals integral 0 to 1 dV, says the volume of the whole solid is what I get by adding up or integrating all of the little volumes. So each little volume taken at a number x, where the slice is taken at a number x between 0 and 1, each little volume has, or each little solid has volume pi x dx. And if I want all the volume of the whole solid, I need to add up all of the little volumes. That's what the integral does. So this is saying I'm going to add up all of these little volumes. Each one of these little volumes is pi x dx. And when I add all of those up, that's doing this integral. So here, this evaluation step, this is giving me the volume of the whole solid. Cool. Your book does have some nice pictures to kind of help you see what the integration step is doing and relate it to the idea of a Riemann sum. So if I wanted to find the volume of a whole sphere like this, I can think of it as being a bunch of little slices stacked up like that. And as the number of slices goes to infinity, or the thickness of a given slice becomes smaller and smaller, you get a more and more accurate representation of that volume. And in the limit, as the number of slices goes to infinity, that becomes exact. And that's when this sum actually becomes an integral. I don't find it especially useful to go through building Riemann sums for these things, because I know everybody hates Riemann sums and they're not super transparent. But that's what's going on. So let's look at one more of these straight up slicing problems, and then I'll introduce you to the two special cases called the disk or washer method. The pyramid problem is a fun one. So we're going to find the volume of a pyramid whose base is a square. With side length L. Oh, L, and whose height is H. So what's this pyramid look like? Okay, well, its base is a square. My art is bad. Its base is a square, and the side length of that base is L, and its height is H. So something like this. And the height here is H. All right, something like that. So that's my pyramid. I want to find his volume. The trick to doing this is going to be to turn the thing on its side and running an axis through it. Now you don't really need to turn it on its side, but it's just easier to draw that way. So I'll call the vertical axis here my y-axis. I'll call the horizontal axis here my x-axis. And I'm going to do my best to think of this pyramid as living in here. Like this. So down here at the point, x is equal to 0. This is my x-axis. And out here where the pyramid ends, x is equal to h. All right. And then the question is, what does a slice of this thing look like? If I take a little differential thickness slice, can I find the volume of that slice? So, do my best to draw this for us. So yeah, what is the volume of that little slice? So looking, this is why I say it's nice to just look at the slice. Again, I'm taking my slice at some generic point x along the axis there between 0 and h. So this is being done at some point in here, which I'll just call x. The thickness of the slice is dx. So this is my little differential solid dv. This dimension is dx. But what are the other dimensions? Like, what is this? What is this? That's what we need to figure out. The game here is going to be to look straight on the side. So rather than trying to draw the 3D picture, I'm going to imagine that I'm turning this and looking straight on the side. Then what I see is just this triangle. Here's where I'm taking my slice. So this is the 3D view of the pyramid. This is the side-on view of that same pyramid. And this is the slice that I've taken out, just viewed on its own. This thickness, we've already said, is dx. But what I need to know is this height. This is going to be a square, right? Because the pyramid has a square base. It has that symmetry running all the way through it. So whatever this is the same. But figuring out exactly what that is going to require a little bit of work. I was told that over here, the side length of this pyramid, the base here, is L, which means that this is L over 2. And this is L over 2. If I'm taking this slice at x, then I need some way of coming up with this distance as a function of x. Any idea how I could find that? Do you see anything that you could do geometrically here? Any sort of geometric arguments you could make? Yeah. Not just any triangles, but similar triangles. Yep, we got everything there we need in the chat. This is good. I don't know any angles explicitly, but I know that this triangle, first is an isosceles triangle. That's nice. There's a lot of symmetry there. But also the little triangle in here is similar to the big triangle out here. Remember that this distance is h, right? In other words, right here, this is x equals h. So this distance over this distance is equal to this distance over this distance. Now, instead of going after that, why don't we just go after this? Because this is really what I want. The slice is still being taken here at x. So this distance is x. We'll say by similar triangles, this over this equals this over this. So I need to label the thing that I'm after here. I haven't given it a name yet. What do we want to call it? I can't call it big L. Call it little l. So by similar triangles, L over x is equal to capital L over h. That's this over this, which is L over x, is equal to this over this, which is big L over h. So remember, this is little l, this is little l, because that cross section has to be a square, even though my art is bad. And now I've got a formula for little l. Another option would be to construct the linear function here that defines the boundary of the pyramid. You could do that, but it just takes a little bit more work than using the similar triangle argument. So I prefer the similar triangle argument, but either one is okay. This relationship that we get from the similar triangles tells me that little l is equal to x times big L over h. So little l, this distance is x times big L over h. This is x times big L over h. Which means that my differential volume dV is this times this. It's little l squared dx, which is the same as x times big L over h squared times dx. It may take a second for you to be able to follow the similar triangle argument. It is a little bit confusing, especially if you're not used to these. Yeah, I know, it pushes my drawing skills too. It's the case that in this class, and even more so in the next class in Calc 3, you'll be drawing a lot of things in 3D. You'll see that my art skills are not beautiful. I don't expect your art skills to be perfect either. Make sure that what you draw conveys the important information. In particular, label things, right? Labels are what save the day if your art skills are not perfect, and nobody's art skills are perfect. But this distance here, this is x. This distance here is little l. And because this triangle, the triangle that I'm like bolding here, is similar to the big triangle, his height over his base is the same as the big triangle's height over the big triangle's base. So little l over little x is equal to big L over little h. And that lets me solve for little l, which is the side length that I need in order to come up with my formula for that slice, dV. Once we have that, we're golden. Because V is always the integral of dV. And I'm going to integrate from x equals 0 all the way out to x equals h. And then dV is the thing that I just did all this work to find a formula for. So the integral from 0 to h of dV is the integral of x times L over h all squared dx. Now, when you square this fraction, you get x squared L squared over h squared. The L and the h are both constants. So this is equal to L squared over h squared times the integral from 0 to h of x squared dx. We're being careful with our notation. Tell you what equality is being continued there. And then this as a power rule antiderivative, so this will be L squared over h squared times x cubed over 3 evaluated from 0 to h. So that is L squared over h squared times h cubed over 3. If you want to write in the -0 there, you can, but the lower limit doesn't contribute anything. When I plug in 0 for x, I get 0 there. And then the h cubed upstairs can cancel into the h cubed downstairs. And so we get L squared h times 1/3. And a really good problem for you to go and do to see how well you understand this and how comfy you are with the arguments we made here. Go find the volume of a cone whose base is a circle of radius r. Very, very similar problem. You can set it up and run through it in exactly the same way. And you'll find that the result is very similar looking. It's a 1/3 r squared times h for the cone whose base is a circle. And I recommend doing that. I think that would be a good follow-up example for you to try on your own to see how comfy you are with this method of slicing. So take a second, make sure that your notes have all the important bits here, that you're capable of reproducing this argument, and see if there are any questions you would like to ask right now, anything you're having a hard time reading or anything you're wondering where it came from. We did, yeah. We just derived the volume formula for the volume of a pyramid whose base is a square of length L and whose height is H. And it turns out to be very similar to the volume for a right circular cone, which is the famous one-third pi r squared H. Because I need my dV here, so I'm taking the volume of this slice and I'm integrating that. And the volume of that slice is the length times the width times this, length times width times height. So that's L times dx is L squared dx. Yeah, cool shit, right? No problem, no problem. These are fun things. And the geometry interacts with the calculus in a really nice way. And that's the goal of these sections that we're doing with the area and the volume, is to kind of help you see the intersection of the geometry and the analysis, the calculus. Other fun things to do here, you can cook up the volume of a sphere, right? That's not a difficult example. The textbook, I think, goes through that example. It's a classic one, and in fact, maybe that's what we'll do for our first official disk example. No, it's too easy. It's too easy. It's too easy. We need to prep you guys for the better stuff. So before we move away, questions on this example, lingering questions, any curiosities? All of our volume problems will actually be v equals the integral of dv. The difference between the methods is how you get the dv. So the slicing method is the most general in the sense that we just say, okay, dv is going to be a slice of my solid, and I come up with the formula for dv however I can, usually using some sort of geometry argument. The other two methods we're going to talk about, the disk washer method and the cylindrical shells method, you'll still be coming up with dv and then integrating dv to find v. It's just that you'll have formulas for dv rather than having to make a geometric argument. So in some senses, what's about to come is a little easier than what we're doing now, because here you have to look at the situation and apply some geometry, and in the others, you'll have a formula. But we'll always integrate dv in order to get v. Cool, yeah. There will be a collection of formulas that you can remember, and as soon as we finish talking about the last method, I will present those formulas to you, yeah. So of course, as we introduce them, I will present them to you, but then at the end, I will recap by showing you the differences between the formulas. So I am going to move away from this example now, and we're going to look at a disk washer problem. So let's find the volume of the solid generated by rotating the region bounded by y equals x and y equals x squared about the x-axis. So if you look at that graph, y equals x and y equals x squared, I'm going to exaggerate it a little bit here. Here's y equals x squared, and here is y equals x. So this is the region I'm talking about, and I want to spin that around the x-axis. So when I do that, I'll get a solid. It's a weird looking solid. Let's see if I can, I'm not even going to attempt to draw this one by hand. It's so wonky looking. But this family of solids that you get by rotating a region are called solids of revolution. Let's see what I get if I search this. Nothing nice here. Okay, so I'll show you the textbook's drawing. This is the textbook's drawing of this thing. So you see the outside is like a cone, but the inside is all bloopy. So imagine you took a cone, but then you make the inside of it like puff out into the cone. That's what we're looking at here. That's the solid. I'll do my best to sketch it here. So it's going to look like this. But the cross sections kind of look like this. And then the whole thing, of course, is like rotationally symmetric. So it's something like this is, oh shit, is what our solid looks like. Right, my art skills are not strong enough to give you a good picture of this solid, so I'm not going to try any harder than that. But this is where the method of disks and washers becomes useful. Right, this is where the disk washer method becomes useful. There's no way I'm going to take a slice of this thing and then like use some sort of clever geometry to figure out what's going on in there and find the little DV to integrate. So what I need to do is think about what happens if I just draw in a little strip here. Instead of rotating the whole region all at once, what happens if I just rotate this little piece of that region? And this is what your general algorithm for solving these problems is going to look like this. First, sketch the curves, identify the region. Second, draw in your strip. Third, imagine rotating just the strip. Then, the thing that's generated by rotating just the strip is your DV. So your little differential solid, notice that there's an air gap here. It's not going to be a disk now. It's going to be a disk with a little bit missing in the middle. Draw a better picture. So if I rotate just that strip, if the strip extended all the way down to the x-axis, I would get a disk like this, but it doesn't. So instead, I get a little washer. The thickness of this strip is dx, so the thickness of this washer is dx. And I have two radii. I have a tiny little radius in here, and then I have a big radius out here. And the volume of this little differential solid is what you get if you take the big disk, which would be pi times capital R squared, and you subtract out the little disk that's been deleted by this air gap, which is minus pi times little r squared. And then you multiply all of that by the thickness, dx. Which can be simplified, and this is how you will remember this formula, is pi times cap r squared minus little r squared dx. Then you come back to this picture. Here's little r, and here is big R. Do you see how rotating that strip gives you that little washer shape? Why that little air gap in here is coming from this little air gap in here? So now I need to come up with expressions for big R and little r in terms of x. But big R is the height from the line y equals x to the x-axis. Big R is the distance from the top of the strip to the axis of rotation. That's always going to be true. Big R is the distance from the axis of rotation to the further end of the strip. And little r is the distance from the axis of rotation to the nearer end of the strip. And that's always true. So this is what's called the disk washer method. So each method has a formula for dV, and then tells you, how to get the little bits in the formula. And this is the most general way to describe this method that will never fail. Yeah, fair enough. So little r is the distance from the axis of rotation to the nearer end of the strip, because it's this little air gap. Maybe if I draw my dV solid a little bigger, you'll be able to see it more easily. Usually I'm working on a big board when I do this. So this is little r, right? It's the space between this strip, which sweeps out my solid, and the axis of rotation. So it's always going to be the distance from the axis of rotation to the nearer end of the strip. And then large r is the distance from the very center here all the way out to the edge. So that's the distance from the axis of rotation to the further end of the strip. In other words, the axis of rotation runs right through this thing. Right? You imagine just revolving this strip, right? Like I could pick this up and spin it around. If I just revolved this strip, there would be a little gap in the middle of the solid created. That is this gap. That is this gap right down here. All right, so let's take a second. Make sure you get this boxed statement down. Make sure you have a nice picture of dV here somewhere with little r and big R and dx labeled. Make sure you have this picture of the graph, and maybe draw it a little bigger even than I did so you've got more room to get in there and label things. And then we'll go ahead and finish the computation. Sorry. Okay. Any lingering questions on the setup before I continue with the computation? The length from the parabola to y equals x, yeah, this length, the length of the strip is cap r minus little r. Yep. Now we don't end up using that anywhere because of the way the volume formula works out. Because we're taking the volume of the big disk and we're deleting the volume of the little disk, we need to square cap r and square little r before we can subtract them. But it is true that the length of the strip there, if that's all you cared about, would be cap r minus little r. But it's not something that we end up using anywhere in the computation. So let me recap here. I'll draw this picture again, maybe a little more exaggerated. I'm going to take this region, plop a little strip in there, and imagine rotating just that strip. The point down here along y equals x squared is x comma x squared. And the point up here along y equals x is x comma x. This is my big R, and this is my little r. And when I rotate just that strip, I get my differential solid looking like this. With that hole in it. The distance from the center to the edge of that inside part is little r, and the distance from my center to the edge of the outside part here is big R. And so the volume of that little differential washer, dV, is pi times cap r squared minus little r squared dx. What is capital R? What is the distance from the axis of rotation to the further end of the strip? So it's going to be this y value minus the y value down here, which is, yeah, x, or x minus 0. Good. And what is little r? What is the distance from the axis of rotation to the nearer end of the strip? That would be this y value minus this y value, which would be, yeah, x squared minus 0, or just x squared. Good. So then my dV is really equal to pi times cap r squared is x squared minus little r squared, which is x squared squared. So that's what we're going to integrate. We can simplify it first. This is pi times x squared minus x to the 4 dx. Therefore, my volume, which is always going to be the integral of dV taken from somewhere to somewhere else. And in this case, I'm going to integrate from 0 to whatever the x value is here. The place where these two curves intersect is 1, 1. So this will be the integral from 0 to 1, the smallest x value in my region to the largest x value in my region, just like the area problems, of dV, which is the integral from 0 to 1 of pi times x squared minus x to the 4 dx. And that's not a terribly tricky integral. The pi pops out. And then x squared integrates to x cubed over 3 minus x to the 4 integrates to x to the 5 over 5. And this needs to be evaluated from 0 to 1. At 0, both of those terms are 0. So really I just get pi times 1/3 minus 1/5. Which is 2/15. Is that right? 5/15 minus 3/15. Yeah. So this is 2 pi over 15. So this is your typical disk washer problem. We call it the disk washer method because this thing is like a disk or a washer, right? If little r happens to be 0, if the strip extends all the way to the axis of rotation everywhere in that region, then you end up with a differential solid here that looks like just a straight disk. If the strip has a gap between it and the axis of rotation anywhere in that region, then your little differential solid is going to be a washer shape like this, like a punctured disk or an annulus. It's the mathematical term. So cap r is this y value minus the y value down here. Now this point is x comma 0. Remember, it's the distance from the furthest end of the strip to the axis of rotation. So that's the y value here minus the y value here, which is x minus 0. In other words, this distance right here that we've labeled as r is just x. How did I know the point of intersection? It's something that I happen to know off the top of my head, that x squared and x intersect at the point 1 comma 1. Otherwise, I would have had to set those two equal to each other and solve. But yeah, y equals x and y equals x squared, they touch when x is equal to 1. It's something that I just happen to have known. Sorry, I kind of shoved that in there. So yeah, 2 pi over 15 would be our final answer. If it wasn't given to you by me or by the problem, then you would need to have solved for that intersection point to find your upper limit of integration. And the r's are the tricky thing to come up with. And the trick to coming up with them is to remember first the definition that I gave you. Where did I put that? This boxed statement. This is your key to finding the r's. So always remember this. Right? This is what the disk washer method is. The difference between this method and the other methods is just how you come up with dV. So for the disk washer method for section 6.2, this is what you need, right? This and the slicing stuff that we've talked about, but there are no real rules for the slicing stuff besides finding a formula for the cross-sectional area. Okay. So how are we doing on time? Well, we are right about at the perfect moment to stop. So I think I may go ahead and stop today's lecture here. And then, not tomorrow, but Wednesday we'll pick up with a little bit more of these disk washer problems. And then I'll also show you the method of cylindrical shells. Really quick before I go, I have one fun problem for you. I lied, I have two fun problems for you to think about. So first, find the volume of a cone whose radius at the base is r and whose height is h. And do this as a slicing problem. Okay, do this the same way you did the pyramid problem. And then one other fun problem to think about, and I'll ask you to think about this also in terms of the new method we're going to learn next time. Take the graph y equals ln x. Take the region between 1 and e, that's this region, rotate it about the line x equals -1. Find that volume. Or at least set up the integral. I don't remember off the top of my head whether finding the volume exactly here requires an integration method you don't know yet. But this is a problem that, hint nudge, tends to show up on my exam 1 in some form or another. So where the axis of rotation is not one of the coordinate axes, here we're rotating about the line x equals -1. And so you would be inclined to draw your strip in like this for this one, which means you're going to have to think a little bit about how to get cap r and little r. It's going to require a bit of work, but your thickness here is a dy thickness. So your integral will be a dy integral. And on Wednesday, I'll talk you through some problems like this. So the first problem would be a good one to tackle between now and Wednesday. Of course, make sure you finish homework 1, and I'm going to be releasing homework 2 a little later today. I'll probably do that as I wait for my cat to be seen. And then yeah, so go ahead and work on this problem and the first few problems of homework 2, and then save this one for after class on Wednesday. You said you wanted to see this example back on the screen, so there's that. And then the only last thing I'll ask for you guys to do is to type the word "here" in the chat so I can keep track of attendance. Once you've done that, you are welcome to sign out. Remember, I will not have my normal office hour this afternoon, but I am available through Canvas if you need to talk. If you have any questions, send me a picture of your work, and we will move forwards from there. Are there any last questions? Go back to last example. My brain hurts. Yeah, the brain hurting will get better, and I'm fairly confident things will go well at the vet. But thank you for your concern. I appreciate that. It looks like pretty much everybody has signed in. Yeah, so here are the recommended extra problems. Find the volume of that cone by slicing, and then take the area bounded in quadrant 1 by y equals ln x from x equals 1 to x equals e. Rotate that region about the line x equals -1. Try to set up an integral for the volume of that solid. I will work through this one on Wednesday, or at least I'll prime you for it on Wednesday. We'll look at some situations where we use the disk washer method and a horizontal strip. But yeah, at your own speed, play through these problems. Be aware that the second one is something that shows up on my exams from time to time. All right, I hope you guys have a lovely rest of your afternoon. And like I said, if you need to get a hold of me for any reason, send me a message on Canvas, please. All right, thank you, Sam. Take care, guys. All right, let's get that key. Ham.